for calorimetry. Calorimetry is just the measurement of heat flow, so we're going to do some calorimetry labs, 2 of them actually. And to do that, we're going to use a calorimeter. Calorimeter is just the device used to measure the heat flow of a chemical reaction. Now, calorimetry is dependent on this property of water. Okay? In order to change the temperature of water by 1 degree, it takes a lot of energy. Other substances like metal, if you touch metal outside on a cold day, it feels even colder than the surrounding air. It's very easy to cool off metal or warm it up. Okay? It doesn't take a lot of energy to do that. For example, you pull out something out of the oven wrapped in aluminum foil. You can touch the aluminum foil pretty much right away as soon as you pull it out of the oven because the aluminum changes temperature so quickly and it goes back to room temp so fast. The food, on the other hand, which contains a lot of water, it stays hot for a very, very long time. So this is why even though it's hot in the spring, you still can't go swimming because the pool's too cold. Water takes a lot of energy to change temperature. So we use that a lot in calorimetry. So calorimetry involves just figuring out the enthalpy change of a reaction. It has to be the enthalpy change, though. We can't ever know exactly how much enthalpy the reactants have right now at this moment and then how much the products have afterwards. What we can do is measure the change, though, in their enthalpy. And so to do that, we perform these changes, whether physical changes or chemical changes, in a calorimeter, and the system, the reaction, is surrounded by water. And we just simply measure how much the water changes temperature. The water is not going to change temperature a whole lot because water needs a lot of energy to do that. So we indirectly measure the surrounding water to figure out what's happening with our system. Now, some reactions involve combustion, like this one. Now, we can't do this in a lab. We can't figure out the enthalpy of a combustion reaction because in order to do that, you need what's called a bomb calorimeter, this fancy machine. I'll explain how it works live in class, and I'll explain what I use this for in the hazmat lab. But we don't have one of these. So instead, we're going to do reactions like acid-base reactions where there's no fire or anything. And we can do that in simply a styrofoam cup, and it works very well. So we'll have really simple calorimeters. Alright, so to do all this, there's some standards and some facts that we need. One is heat capacity. The heat capacity is just the amount of energy it takes to change something by 1 degree Celsius or 1 Kelvin. It's nice that we can kind of interchange Kelvin and Celsius here, because while they're not numerically equal, 0 Kelvin is negative 273 Celsius, each increment is the same size. So if it has a 5-degree temperature change, it would have a 5 Kelvin temperature change as well. So heat capacity is represented with the capital letter C. And you could figure out, say, an experiment, you could figure out the heat capacity of a ring or something. Well, that might be interesting, but it's not. Heat capacities aren't that useful. What we tend to use more often is the specific heat capacity and the molar heat capacity. Here, it's the same thing as the amount of energy it takes to change something by 1 degree, but it's a mole of that substance. So molar heat capacity is the heat capacity, the amount of energy needed for 1 mole of the substance to change by 1 degree. So the symbol is still a big C. We just write molar after it. Molar heat capacity. And the units then, instead of just being joules per degree Celsius, it's joules per mole per degree Celsius. And then the other one we use is the specific heat capacity. It's represented with the letter S. Instead of per mole, it's simply per gram. Okay, it's how much energy it takes to change 1 gram of a substance by 1 degree Celsius. So here's the specific heat of water. Go ahead and memorize it. It's 4.18. 4.184 if you want more sig figs. We're going to use this a lot, okay, because we're going to frequently be figuring out the enthalpy change of a reaction by doing it in water and then measuring the energy change of the water. So that is a really high heat capacity. It takes quite a bit of energy to change 1 gram of water by 1 degree Celsius. It takes 4 joules. In comparison, nickel, I think, has a specific heat capacity of 0.44. Not even a whole joule. Less than a half a joule is needed to change a gram of nickel by 1 degree Celsius. So So metals have really low heat capacity, but water has a really high heat capacity. So when we do these experiments, you're going to see your system, like a chunk of metal, change temperature a lot. But your water, because it has such a high heat capacity, it won't have a big temperature change, and it should. That's normal. Alright, so there it is visually. It takes that much energy to change a gram of water just to warm it up by 1 degree. That's why your pool's still cold when it's hot outside. Alright, so let's do a math problem. How much heat is needed to warm up 250 grams of water, about a cup, from 22 degrees Celsius, which is about room temperature, to near its boiling point, 98 degrees Celsius? The specific heat of water is 4.18 joules per gram per Celsius or Kelvin. I don't care how you write it. Either way's right. This is kind of like the Dr. Seuss problem we started out with. You're given these numbers, you're given that number, you're given that number, and there's an algebra formula for this, and I promise I'm going to show it to you here in just a second. But my point is, you don't need it. You can just look at the units. You guys are good at algebra, and just cancel out the units you don't need by dividing. Okay, so we have the Kelvin or the Celsius is the change in temperature. So first we need to figure out the change in temperature. So final temp was 98 minus the initial temp is 22. So there's a difference of 76 degrees. Okay. We're wanting to know how much heat it takes to change 250 grams of water by 76 degrees. We know this, that it takes 4.18 joules to change 1 gram by 1 degree. Okay, and remember, whenever you see a something slashes something, you set that up as a fraction, as a conversion factor. Okay? So we have joules on top, and we have joules on top, and that's what we want to know, how much heat. We want joules. We have grams on bottom. We want to cancel it. So how would I cancel grams since they're on the bottom? I'd multiply by grams. Multiply by that 250, and then grams would cancel. I also want to cancel the Kelvin or Celsius. I want to get just joules. So once again, I would multiply it so that the unit would cancel, and I'd be left with joules. So it would just be this number, the 4.18, times the 250, times the 76. Voila, that's how much heat it would take. Everything cancels with the joules. Hopefully you followed that. If not, here's the formula. Q equals SM delta T. I just say QSMAT for this one. It's the QSMAT problem. Q is heat, that's what we're trying to figure out. S is the specific heat of the substance. Here that is, the specific heat of water is 4.18. M is the mass, 250 grams. Delta T is the change in temperature, that's 76. Plug and chug all those numbers in there, and we get 7.9 times 10 to the 4th joules. It would take quite a bit of energy to change a cup of water from room temp to about boiling. You know this. You know how long it takes to boil water on the stove. Alright, so there it is, how to do it just reasoning-wise, and how to do it using the algebra formula. Now, what's the molar heat capacity of water? Okay, we know the specific heat capacity of water. That's per gram. We want it per mole. So we just want to cancel this gram that's on bottom and convert it to moles. So we know there's 18 grams in a mole of water, 18.02 to be exact. Do we need to multiply or divide by that? By the 18. So I'm going to take the 4.18. Should I multiply by the 18 grams or divide by the 18 grams to cancel grams and convert it to moles? Well, because grams is on bottom, we're going to need to multiply by it. So there's my specific heat capacity. I'm wanting the molar heat capacity, so I simply convert my grams to moles. And so instead of 4.18 joules, it's 75.2 joules per mole per degree Kelvin. And then everything's animated for some reason. Okay, so the formula for your basic calorimetry stuff, you know, how much heat does it take, blah, 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 is QSMAT. Heat equals the specific heat times the mass in grams times the change in temperature in Celsius or Kelvin. Delta T means change, so final minus initial. How it ended minus how it started. Now, be careful of the signs of Q. Sometimes you'll get a negative Q. Okay, that means it lost heat. and other times it'll be positive, so pay attention to that. And then the mass has to be in grams, and the specific heat is in joules per grams degree Celsius. You can also use Kelvin. The only thing that won't work is the Fahrenheit. Alright, so now sometimes you're going to be doing a calorimetry problem that doesn't simply involve just water or just a chunk of metal. You could be working with solutions like a cup of coffee or an acid solution. So what we do when that's the case, we assume the specific heat of the solution is the exact same thing as water, because whether it's coffee, soda, stomach acid, whatever it is, Windex, it's mainly water still. So we assume that the specific heat is the same as that of water, it's 4.18. And we also assume that the mass per volume ratio is the same as water, the density is the same as water, so we assume that there's 1 gram for every milliliter. So sometimes it'll tell you you have a 50 milliliter solution, and it won't tell you the mass of the solution, because you're supposed to assume that, like water, 50 milliliters of the solution would be equivalent to 50 grams, because the density is 1. So that's a little shortcut. So if you had a 225 ml solution of 2 molar hydrochloric, okay, you would have the specific heat as 4.18, that should be 4, just like water, and you would assume the mass is 225 grams, since the volume is 225 milliliters. Alright, so let's try an aluminum problem. Aluminum has a specific heat of 0.902, okay, quite a bit less than the 4.18 that water has. How much heat is lost when a piece of aluminum with a mass of 23 such and such grams cools from a temperature of 415 to a temperature of 22 degrees? Okay, it's a case math problem. We know we have to figure out the change in temperature. What is the 415? Okay, Celsius. Is this the initial temp or the final temp? We got to make sure we get this correct. It cools from a temp of 415. So that's the initial temperature. And it ends up at a temperature of 22, room temperature. That's the final temperature. So to get the change in temperature, we take the final minus the initial. So we're going to take 22 minus 415. And we'll end up with a negative change in temperature. And that's okay. That means we're going to have a negative heat. Heat was lost. We had a really hot piece of metal and we let it cool off. So that makes sense that we're going to get a negative Q on this one. Think about that. Think about what kind of answer you're expecting. Alright, so read the question, figure out what it's asking you, and try to picture it. Here we're taking a piece of aluminum out of a hot oven, okay, and letting it cool off to room temperature. And so imagine it losing heat to the environment as it cools off, and you'll know then to expect a negative Q. Now I like to just list out what all the numbers I've given in the problem, and that usually makes it clear to me what formula I need to use. So the question asks how much heat, so what's the Q? We know the mass of the metal, we know the final and initial temperatures of the metal, so I went ahead and figured out the delta T is negative 393. And then the specific heat of the metal is 0.902 joules per gram degree Celsius. Once again, we could just multiply and divide the units to get them to cancel, or we could use the equation, use the formula, Q-SMAT. So now we just need to plug and chug. S was 0.902, the mass of the substance was 23-ish, and the delta T was negative 393. Okay, notice that my joules per grams degree Celsius of my specific heat, well, the grams is canceled because I'm multiplying by grams, and the Celsius is canceled because I'm multiplying by Celsius. All I'm left with is joules, which is what I want. Okay, and I would round that to like negative 850 for sig figs. Yeah, to really show this in 3 sig figs, which is what it needs, I would have to put it as 8.50 times 10 to the 10 to the third. I'd have to put it in scientific notation, but I didn't mess with that here. So we got a negative answer. That makes sense. The hot aluminum cooled off and released heat. 8,500 joules of it. So does it make sense that everything canceled but joules? Yes, because that's what we're looking for, just heat energy. It makes sense that it's negative. Alright. Out of time. This is another problem just to save it. I'll pick up where I left off.